Welcome to the optical communication course. Today we see that next model of a optical communication, that is model 5. So in which we will learn that the optical transmission system, that is a model 5 title. So in which we see that a two part of this model transmission system and a optical amplifier. So in a transmission system we will see that how your link is there for this optical link, what are the requirements, and then in optical amplifier we'll see that a various amplifier means your signal transmitting from the source through optical fiber. Then at a receiver, if the signal strength is low, so we need to amplify that received signal. So that's why we require a amplifier. So that is about the optical amplifier part. So we start our discussion with a part A, that will be a transmission system, and we start here with a topic that is a point to point link. Now for the point to point link, how your optical system transmission takes place. So we'll see that for a given transmission system, we require a bit or a data is to be transmitted. This one is belongs to a information source, and then that information that will be given to the optical transmitter, is to your light source. Then we have a optical fiber, and after that we have a optical receiver, and then after that we'll get the data, and that get the data is to be delivered to the user. So now in between this, we say that this one is your optical fiber. What type of optical fiber we consider here in a transmission system? So we need to know that fiber, based on that what will be your total information. So now why designing any system or designing any link, we need to know about that what are the various components we are using in this system. That is about your data. We can say what will be the size of the data and what data rate required, and then what are the various transmitters we are using for this design. That is a source, whether that source is LED source or a laser source is there. Then a optical fiber, and then a optical receiver. Now generally if we see that the main important part of your optical link or your system, transmission system, is the optical fiber, because in a design we should know that that fiber will support that data rate or not, and how long your distance or how long your signal is going to be transmitted there. So that's why a important factor is about your fiber, and then we, according to the fiber, then we can choose the source, and then we require the detector. So means in a designing any link, optical transmission link or a point to point link in a optical communication, so we need to know about these three factor: what will be your fiber, what will be the source, and what will be the detector. So we see that the requirement of this link, so it will transmit the signal for the desired direction. So now what are the various requirements from this link or this system? So it is about, we can say that, what will be the distance to be transmitted, your signal is to be transmitted. So means we can say that a transmission distance, so that much we use for transmitting the signal there. Second thing is about data rate, or we can say that channel bandwidth, or you can say that simply a bandwidth. Okay. Requirement, another requirement is about what will be the bit error rate. Now these are the requirement for your optical link. These are the requirement for your optical link. Means while designing the system or while analyzing the system, so we need to know about these particular factors. Or designing the system, we require what, for what length we are designing the system, at what rate, and what will be the expected bit error rate from the system. So already we learned that a BR, bit error rate performance, for the optical transmission link, we say that 10 to the power minus 9, that will be desirable. So now these are the main requirement for the link, and then to achieve that particular requirement or to fulfill that requirement, for this optical link we require a specific component, and that specific component that will provide you the transmission distance, that will be a fiber, then the data rate, and then that is about transmitter side, then bit error rate at the receiver side. So we can consider here, so what type of a optical fiber we are going to be used in the design. That optical fiber, we say that it can be of a single mode, or we can say that a multi-mode optical fiber. So when we consider that a fiber, whether we can say that it will be a single mode or a multi-mode, then the requirements are, for this given particular fiber, it will be about a core size of the fiber. So that core size of a fiber will tell you what will be the supporting modes, or what source is to be used for this particular optical fiber. So that's why we require the core size of our optical fiber. And then another is about a co-refractive index profile. Co-refractive index profile, and that co-refractive index profile will tell you what will be the a dispersion or what will be the attenuations and all. Then we talk about the bandwidth, or we can say that because data rate is depending upon that bandwidth, or it is depending upon that a dispersion there. Then what will be the attenuation for your system? Then what will be the numerical aperture for the, or we can say that a mode field diameter, that is MFT. Now if you see that this all the component, so system requirement is about what transmission distance, then that transmission distance that will be belongs to your fiber, because we say that for a given particular fiber, that attenuation or we can say that distortion is depending upon that length of the fiber. So transmission distance automatically we need to see that what type of fiber we are using in the design. So that's why a core size is an important factor, and all other factors, attenuations, numerical aperture, again related to your transmission distance. So that core size, if it is a small or a large, then your supporting mode will be improved here, increase. If the size is increased, the modes will be supporting, that will be increased. If you use the core size of a fiber, if it is a small, then we can use, or it will support a single mode fiber. If it is a large, then it will support a multi-mode fiber. Then for this large and this small, then it will support that what type of a source we require for this design. Then the core refractive index profile. That core refractive index profile will tell you a distortion for that particular refractive index, because operating wavelength is depending upon that, or that distortion in a system, it is depending upon that a fiber and a core refractive index profile, that will be again depending upon the wavelength. So that factor means we can say that dn by d lambda, that is square something equation, and according to that we can talk about that loss distortion. Means that fiber will work for a given particular wavelength, or it will be good for that particular wavelength. So that's why we need to know about the refractive index of the fiber there. Then the dispersion or a bandwidth, that is data rate, it depending upon the dispersion. Okay, you can say that bandwidth and both the factors are nothing but common or same. In the case of a dispersion, if the length of the fiber increase, the dispersion increase. And then again, dispersion have a two factors. We say that will be intermodal dispersion and intramodal dispersion. Again, all this, or again one more dispersion, that is waveguide dispersion. That all these dispersions, if you see that it is depending upon that the optical fiber material. So if you say that material, then again it will come to the refractive index profile or refractive index of the fiber. So then this index profile, co-refractive index, then index profile, if we have the gradient index fiber, then in that case, what will be the profile index for the given particular fiber? So means we can say that if we have a step index fiber, then this one is about a core size, and this one is about a cladding. Now this one is the changes. This one we have say we can say that core. This one we can say that a cladding. But in the case of a gradient index fiber, that refractive index, because that cladding is same, but gradient index fiber, that refractive index depends upon that what are the various steps. So now that if that profile will be a parabolic or that profile will be triangular for this refractive index of the fiber. So according to that means we can say that index profile, that is nothing but parabolic or a what will be the shape of that co-refractive index profile. So according to that the dispersion will be reduced. So if you want to remove the distortions, then you can prefer that gradient index fiber. Then attenuation. Attenuation in a given particular fiber is depending upon that what will be the total length of the fiber, and then in between that optical fiber how many connectors we are using. According to that your attenuation will be changes. Then the numerical aperture or a mode field diameter. We'll see that first a core of a optical fiber. You can say that this is nothing but a optical fiber. We say it is nothing but a core. And for this particular core, that numerical aperture is depending upon that acceptance angle of the fiber there. So that is we can say a numerical aperture. So in terms of a source, how your mode will be reflecting across this fiber core. This is about a core of a fiber. So now how your signal will looks like. So this one. So in that case, this is nothing but a mode field diameter of a fiber. In a, another way, if I draw, suppose this one is a cladding, this one is of a core of a optical fiber, for example, this is about a center axis. Generally, what happen here? So it has a maximum intensity at the center. So this one, mode field diameter is nothing but what? What will be the this distance? That is nothing but a mode field diameter of a fiber. So what will be the intensity? What will be the mode? Okay, so that is about a mode field diameter of a optical fiber. Then next requirement is about what will be the source. That source can be, we can say that it can be LED or a laser. Then for the given particular optical source, what will be the emission wavelength? And that attenuation factor, as we say earlier, it is varying based on the wavelength there. So for a given particular fiber, so in which window we using that a source, so that attenuation will be smaller there. So generally, if we say that for a fiber that is 850 nanometer, if we go for the plastic, and if you go for the glass, so 1350 and 1550 nanometer wavelength will be supported by this optical fiber or this particular source. So then what will be the wavelength? So 850 nanometer, if we go for the plastic fiber, then LED source is suitable. So according to that, you can see that what will be the emission wavelength for the given particular source. Then a spectral width. So means from for a given particular source. So what will be the frequency supporting? So that is about, you can say that F1 to Fn. That this belongs to a spectral width of a optical fiber. Because from the given particular source, it will transmit the signal with the different frequencies f1, f2, f3, fn likewise. So according to that, the signal get generated. This is likewise. Okay, this way. So we can say that what will be the operating frequency f1 to fn, so that we can find out what will be the spectral width of the source there. Then output power. Output power means what? Even if we say that we have a good optical fiber, it will support for long distance. But again, we should know that the source to be generated that much power level, so that it will be transmitted to the another distance. Okay. So means optical power is again a requirement. But we could not increase the optical power more than the supporting level of a optical fiber. If we increase the optical power, then a scattering effect occur in a optical fiber, and due to the scattering, then again we say that that will be the loss to the optical fiber. So loss is signal distortion due to the scattering, very light scattering, Raman scattering. If we increase the optical power, then scattering occurs. So that's why we should know that what will be the threshold value of a optical power to be transmitted through this optical fiber. That's why a output power. Then effective radiating area. So effective radiating area, if supposed to be, we consider that a source LED suppose. So then whether it will be transmitting the power, that is about a surface emitting LED, or we say that a edge emitting LED. Likewise. So this is about a edge emitting LED. So likewise. So according to that, what type of a source we are using, and what will be the effective area or effective radiating area, so that we can couple fly lead of a optical fiber or a small optical fiber directly nearby, we can connect to the source. So that's why we need to know about that what will be the effective radiating area of a optical fiber. Then a emission pattern. So in the case of, we say that emission pattern, so we need to talk about that whether it will be emitted and what will be the emission pattern of the source there. So if it is a current or a likewise, so what will be the emission pattern or likewise. So we need to know about that emission pattern. So that emission pattern, if it is broad or a narrow, so according to that we can choose the fiber of a small core size or a large core size. And then the number of emitting mode means for a given particular fiber that will support a multi-mode now, but we should know that this given source is to be support for the number of emitting mode. So already we say that specifically that spectral width, if it is a large, the number of emitting modes will be large there. That is about a component required from the source side. Then from the detector side, you can say that optical detector, and the requirement from the optical detector side main is about a responsivity. So responsitivity means what? For a given particular optical power or a particular photon, how your receiver will respond for the given particular photon. So that is about a responsivity. So responsivity factor, if you consider that a optical fiber, so it is depending upon that what will be the a quantum efficiency and what will be the operating wavelength. So the quantum efficiency, if you see that for the source it is external quantum efficiency, but for the detector, so it is depending upon that how much is the power detected by the given particular that detector. Means when it will detect the, it will generate that a power. Means we can say that, so from this given particular photon that will be incident on the detector, then it will generate that electron hole pair. Okay, I'll write capital here. So number of electron hole pair generated. Okay, so from the given particular photon. So now based on this number of electron hole pair generated, according to that we'll get the current, and then we'll get that how much will be the power there. So that responsivity of a photodiode or a detector, it is depending upon that what will be the current propagating through it. This responsivity, we can say that it is about that how much is the current, what will be the current generated, based on that what will be the incident power or a optical power incident on this detector there. So that is IP by IN, that is nothing but a responsivity R. And then we say that for the given responsivity, how many number of photon electrons generated from, sorry, how many number of electron and hole generated based on this number of incident photon. That is number of what will be the incident power, then what will be the current generated. That is about a AC responsivity. So now we should know that for a given detector, a responsivity is important, and based on this responsivity, we can say that that power level detected or power received will be increased or decreased. Next is about the operating wavelength. The source will work at what particular operating wavelength, 850 nanometer, 1350 nanometer, or 1550 nanometer. Why this? We say that 850 nanometer, 1350 nanometer, or 1550 nanometer. Because these are the three windows, and at these particular three windows, attenuation is low. So that's why source must work at that particular frequency so that attenuation will be low. We can say that 1300 to 1400, that is about a band. Okay, that can work. So that's why we can say that operating wavelength. And then next about a speed, that is a conversion of that particular photon to this electron hole pair, so that we'll get the current. So that is nothing but a, we can say, a speed there. Then a sensitivity. That sensitivity part, again it is related to that electron hole pair generation, and then again that 5 minimum number of photon incident on this particular detector, so it will generate that a current. So that is again we can talk about that responsivity and a sensitivity part there. So in the system for the optical link, so requirement we say that in terms of what distance, data rate and ABR, and again this particular requirement, so we need to consider that how much is the power transmitted for this particular requirement or for the analysis of the system. So what will be the total power required for the given particular optical power system, so that so your transmitter generate that particular power, it will transmit the signal, means your optical transmitter will transmit the power, and then that much power is propagating through the fiber, and then at the receiver, so that optical receiver receive that particular optical power. So means for a given optical power, what will be the minimum requirement by this particular receiver, so that it will expect that 10 to the power minus 9 BER. That is minimum requirement by this optical receiver. So that we'll get that 10 to the power minus 9 for the given BR. Mean that is about a performance of our system. So now for this performance of a system, we say that PR requirement is 10 to the power minus 9. Then for a given link, ideal condition we say that there is no connectors or there is no loss. So then for each and every component, what are the various loss? So means from the optical transmitter side, so we connecting the source to the fiber. So here we have a connector. Then that fiber that we say that it is supporting for the long distance. Then how many splicing we require in this particular fiber? Then there may be a splicing loss. Then again at a receiver, we have a coupler or a connector. So means how much is the input power, so that a minimum power will be received by this receiver. That is about a minimum requirement. So for this minimum requirement, so how much power is to be transmitted by this particular transmitter? So that is about, we consider the loss at the connector or a coupler, loss at the splice, loss in between this attenuator, attenuation in this optical fiber or loss in that optical fiber. So means all overall loss, if you consider that, then how much will be the power will reach to this optical receiver, or you can say that what will be the minimum power requirement for the receiver sensitivity. So that's why we need to consider while designing the optical link, we need to see that a power requirement. So that's why we need to see that what will be the total link power budget. So means we say that link power budget, that is a requirement, minimum requirement at this particular receiver. So we see that how much will be the total loss in the given particular link. That is about the link power budget. So for a given particular system, we see that what will be the a total requirement in terms of a power. And again we say that that particular power requirement for the source as well as the data as well as the fiber, So all these three components, they will support that particular wavelength, and then they will transmit the signal for the given particular distance there. So means optical link, we supposed to be consider that what will be the operating wavelength of the fiber as well as the operating wavelength of this optical transmitter. So we can consider that wavelength as well as for the given particular optical fiber what will be the distance is required. So now what are the system consideration or system requirement? So that is about, we can say that a link power budget. So we have this in a point to point analysis, there are the two requirement for this link. One is about a link power budget and another is about a rise time budget. So in the rear link power budget, we will talk about that what will be the power requirement, P in as well as P out, as well as the operating wavelength, as well as the losses, all other losses, not only the connector losses, not only the spice losses, all other system losses, because system degrades when we use the component for a long year. And then again, what will be the losses if your system degrades there? And if supposed to be any environmental effect or a temperature effect occur on the devices, then what will happen to the given system? So we see that the requirement in terms of what a power, input power, requirement in terms of output power, requirement in terms of what wavelength and a loss. So overall system consideration, we talk about that its system will work for the given particular window. As we say that earlier, we say that 850 nanometer, 1350 nanometer, and if 1550 nanometer. Now these are about the windows, operating windows. It has a low loss, so that's why we need to talk about that this particular region, your complete system will work in that particular operating wavelength. This complete system will work. So then this system work means your transmitter, your amplifier, everything, all the component in this link, that will be work for this particular operating wavelength. That is about a link power budget. And then we say that is about a transmitter side. But at a receiver side, we need to talk about that what is the bit error requirement at a specific data rate or a specified data rate. So that's why we can say that a BR requirement for the receiver, and then how much will be the power required for generation of that BR at a specified data rate. So then we have the scope here at a detector, that is whether we can use a pin diode or a avalanche photodiode. And then for this particular pin diode or avalanche photodiode, so what will be its sensitivity? Sensitivity means what? Even for the minimum level of optical power, so how your detector respond or detector detect that minimum level of a power there. So that is about a sensitivity. So we talk about that from this point of view at a detector in terms of a sensitivity, and then if we consider that from the source point of view, LED or a laser, then which source is to be used to support that data rate, then we can say that it will support that it, that transmission distance at a given particular cost. If you consider that a pin diode and APD, so sensitivity is large here. Large sensitivity means what? Means it will detect a minimum optical power as compared to the pin. So similarly, you can consider that a light emitting diode or a laser. So in that case, a laser has a narrow spectral width as compared to that LED there. So that's why that LED or laser, they will support what operating frequency is there or what operating wavelength they will support. And then we say that whether it will work for this fiber, that is about a small multimode fiber or a single mode fiber, because if we consider that a LED, we can go for the multimode fiber. If it is a laser, then we can consider that a single mode fiber. Then data rate. If you talk about the data rate, if we consider that a laser diode, the data rate will be higher. But in the case of a multimode fiber, so data rate will be lower there if it is a LED source. So now then we see that for the given particular source, what will be the cost? Because if you consider that a diode, if we use the laser diode, so it requires a complex circuitry, then cost will be increased. If we use the LED diode, so receiver circuit is not complex, so cost will be decreased. So that's why while considering the while choosing the a fiber or while choosing this source, we need to talk about that cost also. In the case of a light emitting diode, so they can work for the multimode fiber. So that's why a light emitting diode people are using. That is about a system requirement, and for the system requirement, we need to see that what will be the fiber, optical fiber, that whether it will be a single mode or a multi-mode fiber, or that multi-mode fiber whether it will be a step in fiber or a gradient fiber, and that fiber choosing that particular fiber, it will depends upon that what will be the type of source we are using and what will be the dispersion tolerated by this particular optical fiber. Means generally we say that light emitting diode, we can use a multi-mode optical fiber, and then we need to know about what will be the core and cladding difference if we are using the light emitting diode. So that's all.